Good morning, everybody that just came on. Um, we're definitely, the clock is not going to be my friend today. And I thought maybe we could get all the way through example 9. But this last part of our objective, which is analyzing the graph of rational functions, it takes a while. So what I don't finish with you on example 9, I am just going to finish up on tomorrow's lesson because 2-7 day 1 is not very long. So I will just put that at the beginning of it. And I did have a note here that in other years we haven't been able to finish it either. There's just so much. Have your graphing calculator handy. And then it also slows down when I ask you questions, which I need to do and I like to do, but boy, oh boy, for some reason that just slows the whole process down quite a bit, and we've got a lot of material to get through here today, so I won't be asking you much today. This one, we had gotten to the point where we were going to be needing some tables to see what was going on with the graph, but we did have a couple of points that we knew were going to be on it, and those were our x-intercept and our y-intercept. So our x-intercept was at negative 21/5 0, so negative 4 1/5 0. And we have a y-intercept at 0 and not quite 1. Now already I know something unique is happening with this graph because it's crossing that horizontal asymptote. And anytime we have a unique graph that's something that we haven't seen a lot before, we usually need to have more numbers in our tables so we can see exactly what's happening. But we'll start off with our normals, which would be to the left of negative 5 here, like a negative 6, a negative 7, and then to the right of negative 5. So we already know what's happening right here thanks to our x-intercept. Maybe we get a negative 3, a negative 2, and a 1. And because, like I said, I can see this is not going to be a symmetric hyperbola, I maybe should see what 5 and 10 look like, because I'm supposed to, on a test, accurately graph all the way out there to negative 10 to 10. So I need to see where that's going to be. So now it's time to get her in the old graphing calculator. And again, hopefully you have your calculator already out, but go ahead and put that one in. Parentheses for the numerator, parentheses for the denominator, because we have more than one term up there. And I'll hit zoom 6 while you finish typing that in. Wowzers, that is a very strange looking hyperbola. So yes, we're going to need more points because there are some really significant things happening in this graph that haven't happened in a lot of the graphs that we've looked at. And one of them is right here. There seems to be a top to that, a hill, which would make that a local max. So before I even start with my table, I'm going to figure out what this local max is and get that written down there in my analyze part. Second trace number 4. So left of the hill, right of the hill, and enter through that. So we have a local max of 1.563 at x equals 3.400. I'm going to write that down. Way down here at local extrema. Local max of 1.563 at x equals negative 3.400. All right. Now I need my table so I can get a bunch of points. Second graph gives me the table, and While you are pulling that up, I've got to get it on my handheld as well so that I can write these down without having to flip back and forth because it takes too long. All right. At -6 and -7. -6 is -9. -7 is -3.5. Now, because this one is unique, I want to go ahead and put those on and take a look at what's going on. And I realize that's quite a distance away from my vertical asymptote. So I would want to know what's going on at like -10 so that I can get a really good curve in there. And as long as I had my table there anyway, I see at -10, it's -1.16. So in the window that we're graphing this at, it's not getting incredibly close to my asymptotes. And that's important to know because, like I said, this is very unique. Now let's go to -3 is 1.5. -2 is 1.222. +1 is 0.7222. 5 is 0.46. 10 is 0.316. So let's see what it's doing on this side. -3, 1.5. But then I realized, wait a second, I found that max. I don't think that was perfectly at -3, 1.5. It was pretty close, but not perfectly. So we better try and put -3.4, 1.563 on there. It's just a teeny bit higher than what we had for -3. -2 is 1.222. 1 is at 0.7. 5 is at 0.46. And 10, so it's definitely getting closer and closer to our horizontal asymptote over there, but it did cross it. So there it is. Now that we have it graphed and we found that little local max, the rest of this information will probably go pretty quickly. So as we approach our asymptote, and the only vertical asymptote we had here was -5. From the left, it's going down. As we come in from the right, going down. Now, domain. Well, we have that vertical asymptote at -5, but that's not a big deal. So -infinity to -5, jump over -5 and beyond. But this one has a really weird range because it's using all these negatives down here, but it's never going to go higher than our highest y value. And that's why when we write that local max, we put that y value first because that's, the top point. We need to know that. So our range is going to go from -infinity to 1.563. And then I realized, well, 1.563, that's actually a point on this graph. How do I tell people that? And how we tell them is by putting square brackets on there and saying, hey, we're actually using this point. We are going to make it continuous by saying x can't be -5 because that's a vertical asymptote. And then we have to look at increasing and decreasing intervals. And for this one, we are doing some decreasing, but then we're doing some increasing, and then we're doing some decreasing. So we can't just circle increasing or decreasing here. We're going to have to write them down separately and then think about where they're at. And this one was decreasing from -infinity to -5. But then, as we read it from left to right, it was increasing until it got right there. And this is about the x-coordinate this time. So that x-coordinate was at negative 3.400. But now with intervals of increase and decrease, remember we don't use square brackets because a point can't be increasing or decreasing. Oh, and I put that in the wrong one. Because that was our increasing. Then we're decreasing again. And again, if you need to put something in between them, well, put a comma there if it drives you bonkers that we don't have anything. And we definitely are starting to see that, no, this is not symmetric. This is not a normal hyperbolic function that we normally see. Now, bounded, we usually just put yes or no on this question. Hopefully you looked at this and said, oh, this one's bounded above. But when we're doing the analyze, we usually just do yes or no. So this one is a no. It's not bounded below. We found our one local extrema, which was our local max. And then limit as x approaches infinity for f of x equals. Limit as x approach, oops, I wanted to do negative infinity and I just wrote infinity down there. So left and right. And again, at this point, it kind of becomes rote, and that's because we know it's going to be those horizontal asymptotes. That's what's supposed to happen here, and it is. So those are going to be our zeros. So really now it takes more thinking to do the vertical asymptote behavior than it does the end behavior because we know what those horizontal asymptotes are supposed to be doing. So now, off to this one. And you look at the polynomials that you have that are being divided here and you realize, wowzers, there is a lot going on here as we start to get those higher degree polynomials. And this one has an x squared over an x cubed. Well, I should be able to do some factoring here. So first things first, factor out that greatest common monomial factor, the 4. And in my denominator, I can take a 3x. Trying to fit all that in there, and I write too big. So up on the top, I'm still hopeful that my trinomial is factorable, and I see that it's not a perfect square, but pardon me. There are two numbers that multiply to positive 12 and add to negative 7. And that's x minus 3 and x minus 4. Then I look at my denominator. Again, not a perfect square trinomial, but two numbers that multiply to negative 12 and add to 1. X plus 4 and x minus 3. And then I see, oh, this is a new thing. This one's going to have a hole because the x minus 3 on the top and the bottom would cancel. So I'm going to have a hole at 3 something. So over here somewhere, and I'm going to write it in between my vertical asymptote and my horizontal asymptote, I want to make note that there is a hole. Because if I don't do that right now, the chances I'm going to forget it when I go to graph are huge. So 3 something. How do I figure out again where that is? Well, what I do is actually cancel out those x minus 3's. And put the 3 in to that and see what you get. So 3 minus 4 is negative 1. 4 times negative 1 is negative 4. 3 times 3 is 9. And 3 plus 4 is 7. Well, that's a nasty little fraction there. Negative 4/63. But basically that tells us it's just a little bit under the x-axis. And if we write it over here with the list of things that we have to put on our graph, well, then we won't forget it. Now, that doesn't mean we don't get vertical asymptotes, because we do. There still were 2 more zeros in that denominator that were not part of the whole, and that was the 3x and the x plus 4. So 0 and -4. Horizontal asymptote, well, that's about degrees. And as we look at these two polynomials, we see there's all kinds of variables in there. But the highest powers are going to dominate this. And that means that our infinity squared over infinity cubed is where we focus our energy. The 4 and the 3, that makes no difference at all. We're talking about infinity being raised to powers, and those numbers are huge. So this will be 1 over infinity, which is going to give us 0 as we go to the right and left forever. So our horizontal asymptote is at y equals 0. I'd like some points beforehand, so if I can, I'd like to get the x-intercepts, which is where y would be 0. Well, that's in the numerator where the zeros are, but not where the whole is. So that's 4, 0. My y-intercept is what I get when I put 0 into the function. But then I remember, wait a minute, I can't do that. That was a vertical asymptote. I can't put 0 in there. So that's going to be a none. So even with this part, when we start to get those higher powers of polynomials, things start to get pretty complicated, and you have a lot to keep track of as you're going through this. And best way to avoid goofing up is get all that good stuff on the graph before you even put it into the calculator. So we need vertical asymptotes at -4 and 0. And we need a horizontal asymptote at y equals 0. But before I do anything else, I want to put that hole on my graph. And that's at 3 and just below the x-axis. And it has to look like a donut hole. And I realize that's really big right there, but I have to be able to see some white inside of that. So there's my hole. Now there were a couple of points, or maybe just one point here. Yeah, just one that we do know are on our graph, and that's 4, 0. So we can put that one on as well. But the rest of this is wide open. You know, we don't know where all of this is going to lead to. So I will definitely need some points to the left of -4. And again, I'm thinking I might have to see what -10 is, since this is starting to be so involved. And then between my 0 and my -4, I'm going to need to see that. And then I'm probably going to need a lot of these on the other side of 0. For now, I'll just put 1, 2, 5, and 10 and see if I can get all of that. All right, time to see what it looks like. So, punch it in if you haven't already. It is quite the monster. 4x squared minus 28x plus 48. Don't forget your parentheses. Divided by parentheses 3x cubed plus 3x squared minus 36x. Parentheses. Zoom 6. Look at that one. Definitely not symmetric. And I see some really unique things happening here, because look at how this is crossing the x-axis, but then it looks like it's coming back down again. So we're going to have to really investigate this branch to see what's going on. We're also going to need to know where that is. That's going to give us a local minimum right there. But let's take a peek at the table first and see what's going on. So second graph, at -4 we see an error message. That's good. We said that was an asymptote. At 0 and at 3, that's important because we said there was a hole there. All right, so I'm going to grab my handheld so that I can get some of those numbers. So this is another time when the technology slows things down a bit. Otherwise, I'd be flipping back and forth between the giant calculator there and this screen. All right, so at -5, we have -2.4. -6 is -1.111. -7 is -0.699. And -10 is -0.3111. Too many decimals. Got a spare. All right, so -5, 1, 2, 3, 4, 5. -2.4. -6, -1.1. -7, about -0.7. And -10. Okay, well, that's kind of normal. I mean, I'm looking to see anything unique that I should really investigate further. That's pretty normal. Make it look like it approaches my asymptotes but doesn't cross them. And then the middle portion there, -3 is 3.111. -2 is 2. -1 is 2.222. Well, like I said, we know we have to find the local minimum there, but let's put these points on. -3, 1, 2, 3, and a little bit. -2 and 2, -1 and 2.22, and probability-wise, the probability is really low that -2 is actually the lowest point for that parabolic piece of this graph. So, second trace, we need Blinky to find that minimum for us. And where on earth is Blinky? So I have to hit my left arrow to get Blinky to even show up. And then I want to be on the left side of the valley and hit enter. And the right side of the valley and hit enter. And enter through guess. Well, there it is. And it's definitely not -22. So -1.657, 1.943. Let's go write that down, way down there in our analysis piece. Local min of, what was it again? 1.943 at x equals -1.657. All right. About -1.7 and almost 2. So, this is not a perfectly symmetrical parabola down here. And yeah, that's a little exaggerated, but that's okay because we have to show that we know that something strange was going on there. And then we'll go back to our table for the other side. 1 is -0.8. 2 is -0.222. 5 is 0.0. Well, we're going to have to round to 0.030. And 10.057. Now that's interesting. Do you see how these numbers are going up? Let's graph that and think about what that means. 1, negative 0.8, 2, negative 0.2222, 5, 0.3, 10, 0.057. So if it's still going up, well, it has to come down at some point. So when I looked at that graph, this looked pretty flat. But because of what I see in the table, I know that, and I'm going to really exaggerate this now, it's going up, and then we know it has to come back down because it has to approach our horizontal asymptote right here. There's a local max hidden over there. So let's see if our calculator will find that for us. Second trace, number 4. And I'm going to need Blinky to jump over to that branch that's on the right side. And it's going up at this point, so I'm going to hit enter for the left. But what I want to do is watch my Y's until I see my Y's start to come down. All right, so 0.55, 0.56, 0.57. Oh, now it's coming down. So I'm watching this to see, hey, there is a local max there. Enter, enter through guess, and there it is. We have a local max of 0.057 at x equals 9.657. So we better write that down way down there in the bottom of our analyze. Local max of 0.057 at x equals 9.657. So we wouldn't be able to make a big deal on the graph here because it's so far out here, but we'll connect up what we can, making sure that we leave our hole as it is. And we have that information about the local max down there with our extrema. So that tells us we know that you know what's going on out there, that there's a local max. So those are some things we're going to have to keep track of as we try to do our analysis here. All right, limits. We have to talk about what's going to happen as we approach -4 and as we approach 0. All right, so as we approach -4 from the left, as we approach -4 from the right, as we approach 0 from the left, as we approach 0 from the right. Let's throw a cough drop in before I start to have a fit. Okay, -4 from the left, going down. -4 from the right, and again, this is the one that feels weird because we're coming in from the right, we're going up. 0 from the left, going up. 0 from the right, going down. So we have all those taken care of, but now the rest of this, it's going to be more complicated than what we've done in the past because we have that hole to think of, and we had a local min, we had a local max. There's a lot of things that we have to keep track of. So for our domain, well, we'll start at -infinity, but we'll get to -4, and we're going to have to hop off the number line and hop back on. And we go from -4 to 0, and we've got another vertical asymptote. And then we're not done, because at 3 we're going to have another issue, because there's a hole there. So our domain in this one has lots of little parts to it. So does our range, because we have a gap. There's a gap here that has to be explained. So our range going down forever, but it comes up and there's this highest spot right over here for the y's, and that was our local max, y value. So our y value for our local max was 0.057. Now, we have to tell people, even though we rounded to get that 0.057, that that was an actual y value on our graph. So that means square brackets. Union with, well, now we need to know what was the y value for that min, and then up forever. The y value for that min was 1.943. And again, we need the square bracket on there to show that was an actual point that we had. Well, if we're going to make this continuous, we got some things we have to leave out this time. We've got two vertical asymptotes, so x can't be -4, x can't be 0, and x can't be 3, because we had a hole there. Increasing and decreasing, well, we certainly probably aren't lucky enough that this is all increasing or all decreasing. Decreasing from left to right, decreasing that changes to increasing, increasing that changes to decreasing. Yeah, this one I forgot last hour all about it. I'm writing all the other ones down, and I forgot about that local max out there. There's a lot going on here. All right, so the first piece we come to is decreasing, and that's from -infinity to -4. Won't be the only one. Next piece, decreasing, but then we reach our local min. So we have to find, what was that x value again for our local min? It was -1.657. So decreasing from, oops, and I put that under decreasing. Of course I did. Oh, that part was decreasing. I'm talking myself out of it here. Yeah, this part is decreasing from -4 to -1.657. All right, then it starts going up. So from -1.657 to 0, it's increasing. And then we get to 0. And it's increasing almost all the time. So it's increasing from 0 to the x value for our local max, which is 9.657. And remember, with intervals of increase and decrease, you don't use square brackets. Points cannot be increasing or decreasing. So you may have noticed that I skipped right over the hole. And yes, that's exactly what we do, because points cannot be increasing or decreasing. So now, at a certain point, it starts decreasing again. And that point was our x value to finish that up for that local max that we had over there at the end. So you can see these get much more complicated when you have those higher degree polynomials in the numerator and the denominator. There's just so much to keep track of. Symmetry. No, the whole thing was just a mess. Lots going on, lots of significant features that we had to look at and make sure that we had graphed properly. Bounded, that would be again a yes or no, and this is a no. Thank goodness we already filled in the local extrema there, but we still have to do our end behavior. which turns out to be kind of a non-thinking piece because we know, hey, that's going to approach our horizontal asymptote, which was at 0. So, granted, slows me down a lot up here because I have to deal with, the technology. I have to make sure that we can see the graphing calculator. Then I also have to do the handheld so I can write down all of those things. But this problem, it's going to take a long time. It has a lot of significant features, and we have to be careful that we catch them all as we're going through all of this. And I wish I could tell you that that was the worst of it. And I think it is. I think this is the one out of all of the problems that we have, the analyze piece to our objective is just huge. There's so much for this. But this is a pretty complicated little rational expression here too, rational equation. So there's a lot going on in this one as well. And this is the one that I'm going to stop after a bit here because I want to end at the same place that I did with first hour. And then, like I said, 2-7 day 1 is a shorter section anyway, so I will just finish this up on the video for that one. So analyze and graph. Oh my goodness, got a cubic over a squared. Wait a second, those get slant asymptotes. So the first thing I would do is my division. And as I'm writing it down, I realize, oh, it's missing an x squared. Yeah, there's stuff that's not here. So plus 0x squared minus 16x plus 0. And then I have to figure out, and this is one of the first times we've ever had to do this, I'm going to need a fraction to multiply this by. Because I need x cubed, and this is 2x squared. So how do you multiply a 2 by something and get a 1? Well, you multiply by a half. I also need one more x. So I'm going to have to multiply the whole thing by 1/2 x. So 1/2 times 2 is 1. That's exactly what we wanted. And x times x squared is x to the third. 1/2 x times 6x will be 3x squared. 1/2 x times negative 8 will be minus 4x. Change the signs and add. And it did what we wanted. The x cubes are gone. So I'm going to put my little 1/2 x right up here. But I'm also going to have negative 3x squared and then minus 12x plus 0. So I have to do this again. And it's a little tougher because I need to get a negative 3 out of it. But it's not if you think about what we just did in this last step. Do you see how the 2's were on the top and the bottom of those fractions so they'd cancel out? I have to do that again. So I'm going to have a 2 down here. And I want the negative 3. So the negative 3 will go on the top of my fraction. I don't need an x this time because I already have an x squared piece right here. So this would give me negative 3x squared. And then again, think of it as top times top, bottom times bottom. So that'll be negative 18 divided by 2, which is negative 9x. And then negative 24, positive 24 divided by 2 is plus 12. Change the signs. And add. And the 3x squareds are gone, so the minus 3/2 did its job. Put that up there. And we have negative 3x minus 12. Now, that is the remainder. I'm not even going to bother writing that down because I want to understand that this, the quotient part of this answer, is my slant asymptote. And on this one, you're not going to see a blank down here for slant asymptote, but on the test, you will. So there'll be an extra blank on here somewhere where you can put that slant asymptote. I doubt we'll forget to put it on our graph because we'll put that up there when we do our vertical asymptotes and our horizontal asymptotes and all of that good stuff. Whew. Well, now I feel like we can start this problem because there's a lot of factoring that we can do. So we factor out that greatest common monomial factor of x, and then we see a difference of 2 squares, and we factor again. Down on the bottom, we can take a 2 out, and we hope that we can factor that trinomial. Two numbers that multiply to -4 and add to 3, x plus 4 and x minus 1. And not only does this have a slant asymptote, it also has a hole. So we have to figure out where that hole is going to be. It's the x plus 4's that will cancel out. So we get a -4. And then let's find the rest of it. So we actually do the canceling. And we put the -4 into x times the quantity x minus 4 over 2 times the quantity x minus 1. So let's see what we'll get. -4 times -8 over -4 minus 1 is -5. So on the top we'll have 32, and on the bottom we'll have -10, which is going to reduce to -16/5. So there's our hole. I'm going to put it over here so I don't forget to graph it. Alrighty, next up, x-intercept. Well, that's what we get when the y comes out to be 0. So that's the numerator zeros that won't cancel. So that's 0 and 4. I get 2 of them this time. My y-intercept, that's what I get when I put 0 into the function. So I'm going to go back here for that, because this is going to be 0 minus 0 over -8. Well, that's just 0, so that makes sense. The x-intercept of 0, 0 is always the y-intercept as well. And then any of our denominator zeros that would not cancel out, that's going to be this little x minus 1 right here. That's a vertical asymptote. Horizontal asymptotes, we don't get any, remember, because this would be infinity cubed over infinity squared, which would be infinity, which doesn't approach a number at all. But we got a slant asymptote to work with there. And that was where I had to end it with last hour. So is there anybody that just wants me to keep going? Because I can do that, and we can go a little farther with you guys. But my plan was really to just stop at the first place that I had first hour. Is anybody against me stopping? Do you want me to keep going? All right, so that's where I'll quit, because then both classes will be at the same spot. I will finish this problem up in the video before at the start of the 2-7 day 1 notes for tomorrow. So I'll get that in there. I really thought this year might be able to make it through it, because after we did 2-5 day 3, I started 2-6 day 1, and I've always had in my notes that you don't have time to finish example 9 if you don't do that. But they're just really large and involved problems. That part of our objective that says analyze has a lot going on. You will be able to do day 3. I wanted to make sure that I got through that slant asymptote so that you could do everything that you see in day 3. But before I leave today, at the end of the day, I will make that video for tomorrow. So if you're feeling like you want to see the end of example 9 before you do the homework, it'll be done by, I'll probably have it in by 5 p.m. So there you go. Have a great day, everybody.